what am I doing here? All right, let's give that a look. All right, that's kind of what I expect. Nice titles. Okay. So let's just yeah, let's keep doing this. Where were we? Okay, raid marching. So we need a march function that does a loop, and in that loop it uses a get distance function, which gets the distance from a point in space to any geometry in the scene. So any geometry in the scene, right? It's the distance to the scene, hence scene SDF. So let's do let's see, float SDF scene, and we'll say vec3 is point, and vec3 angle or direction. And do we want to do it like that, or do we want to call it like origin and vec3 dir like that? I don't know. Okay, so in here, for int I equals 0, I is less than max steps, so we'll do 100, and we'll just do like max steps like that, just because I don't feel like writing defines right now. And then I plus plus. Okay, and then within here, the first thing we need is, I've seen this done multiple ways. We're going to use the way that uses the least amount of variables. So, the origin is going... So we're going to actually move the origin. Which you might not like that. I don't know what's more error prone, I guess. Okay, so orig equals orig plus the dir times the distance. Dir and dist kind of look the same, so we'll just do dir times len, like that. So that just looks a little bit better. And then right here we'll have float len, distance to scene. Okay, and in order to get this length, well, we're going to start off as just having it as 0. So we're just going to add 0 the first iteration. And then we're going to say that len equals SDF march. And this is our ray marching. I'm not going to call it ray march. I'm just going to keep it as short as possible. So SDF march for sign distance function march. And then let's just, can we zoom in here? Yeah, that's not really doing anything for me. Okay, so sine distance function March, we'll use the origin, and that'll give us back a length. And if the length is less than or equal to or len is greater than equal to max len, and that's not quite right. That's not quite right. Let me think about it. Yeah, let's just, I changed my mind. Okay, then up here we'll do a define max steps as 100. Define min len as 0.01. Oh, you know what this is? Min len is the this is minimum surface distance, and define and this one right here is the max distance from origin. Okay, so now that I kind of see that it's kind of done that way, makes me want to rethink how I'm doing this. So I'm gonna say float curlen and float, let's say curlen and all len, compounded distance from origin. Okay, and then right here we'll have well, this is getting out of hand. And this is actually Vec 3 current origin equals org. So what we can do here is current origin. It started us off at org, and then instead of org plus, we're gonna do org plus, but then instead of dir times len, we're gonna do dir times all len, like that, and all len is also 0. And then the current length to the scene using the current origin. And then down here we'll do all len plus equals the cur len, like that. Okay, and so then it's, if the current length, if we're like really close to the surface, we're gonna bail out. But then also, if this current length is is like way too far away. So if the current length is way too far away, then we could also bail out. Now let me think about that. Yeah, okay, I think I'm okay with it like that. Because you might want to say, should all len be here instead of cur len? Because I've seen it written slightly differently. But I think that's good. So let's look at this. So we have SDF scene, so it's the sign distance function to the scene geometry, and we're going to take an origin in space. So that would be like your eye position, and a direction. So together, these 2 points make a ray, right? Because a ray is a point with a direction. And so we're going to cast that into the scene. First thing we're going to do is we're going to set current origin to the origin. And this is so that we can update current origin while keeping the original origin the same. And the way we can do that is right here. We are just going to always start from the origin and then go in a certain direction based on the length of the compound length that we have collected so far. Okay, so this looks good here. Cur len equals SDF March with the current origin calculated up there. The first time current origin is calculated, it'll be orig plus 0 because all len starts out at 0. So that looks good to me. If cur len is less than min len, or cur len is greater than or equal to max len, I don't know if you want the min len to be a less than instead of a less than or equal to, or greater than or equal to. I mean, that's an off by 1 error kind of thing. I don't think it really matters what you use. I tend to like to be inclusive when I'm using ranges, so I always use equals. And then right down here, we're going to compound the length. We got this iteration with a collection. We're going to accumulate the length. And this is all len right here is how far down the ray we need to go for the next comparison. So that looks good to me. As far as syntax errors, I'm sure I did something stupid. So let's just hit the compile button here. So yes, we didn't return anything. We did all the math, but then we didn't return anything. So what do we want to return here? Are we just returning if it's a hit or not, or are we returning something slightly different? I don't really know. I guess we should return if it's a hit or not, and if it's a hit, it should be like a 1, and if it's not a hit on geometry, it should be a 0, right? Because then we can, if it's geometry, we can multiply it with something else to get some type of result on screen, and if it's did not intersect any geometry and went into the void, it should return a 0, because if we multiply that 0 by something, we still end up with nothing. So let's think about this. If we're doing that, we don't really... The color of something really shouldn't change if it's further and further away. Yes, the color of something should not change if it's further and further away. And this is... Okay, so now I see why this needs to be something different. Okay, so cur len is currently how far away a point is, and cur len ideally should be getting closer and closer and closer for every iteration of this for loop. And if this is getting smaller and smaller and smaller, then, you know, we'd never hit this. Like, maybe if on the first loop it's too big, it would bail out and work correctly. But what we really want is the total distance from this origin. And the distance from the origin is based on all len, right? Because origin plus some type of offset from that origin direction times all len. So, okay, so now I see why it was done differently in a tutorial I was watching. I thought something looked off there. Okay, so now that I have that, we can go back to thinking about which one of these lengths should we be returning for a result. And I'm thinking, well, this thing can be all over the place, and also you could possibly hit something that is 50 units away or hit something that's 70 units away, but if you hit it, you hit it. I don't think you should return a drastically different different color based on that. So if if it's a hit, it's going to be really close to 0. So with that said, if it's a hit, it's going to be really close to 0, so we need to invert that. So we're going to return float 1.0 minus the current length. So that way, when we hit geometry, this is going to be very close to 0. So let's just say 0 to make it simpler. So when it's hit geometry, it's a 0. And then 1 minus 0 is 1. So we're just inverting the value. So that way, a geometry hit will yield us a 1. Whereas if the geometry isn't hit, where curlen is like really, really, really far off, it's going to return... let's say really far off is a 1, 1 minus 1 is 0. Now, obviously, that's this curlen could be something bigger than 1.0. So what we'll do is we will do a max 1 curlen like that. Okay, so that way we're capping it in the range of... curlen, we're not going to allow it to go above 1 when we're returning a value, but curlen is going to bail out if it goes below minlen, and minlen is pretty much near 0 anyways. Now, if we want to, we might want to be more explicit. So let's do min 0. Hold on, my bad. We don't want to do max 1.0. We want to do min, right? So min, and this is our upper limit is the lowest value, right? If this is infinity and this is 1, well, we're doing min, so we get back 1, and then we'll do max 0.0. We might as well cap it on the bottom as well. And you know what? I need to indent a little bit, because this is... I don't like indentation all over the place. I need it manageable to where, like, I understand where that indentation is going. So we got 2 here, return float, and then we got 2 down here. This just makes it a little bit easier for me to keep track of the parentheses without brace highlighting, right? Because brace highlighting is nice, but sometimes you don't have it. So max and min, we can space out max and min a little bit, like that. That way we can have these 2 parentheses here paired with these 2 here, and that just makes it more readable for me. Okay, so basically it's just invert So this is basically what we want. We want 1.0 for a hit, 0.0 for a miss, right? And I do want to allow for like gradation, and that's why I didn't just do a strictly return 1 or a 0. Because I think we might get some, I'm pretty sure we'll get some anti-aliasing benefits if we do not do that. Now, as far as correctly normalizing this, right? Because if max length is like, you know, this number all the way to 100, should we be dividing this by the max length? I don't know. Let's not try to over optimize it yet. So let's see. What do we have now? Cannot convert from const int to high p float. So I do this all the time. 0.0. So if you don't include a decimal point, it will not be interpreted it'll be interpreted as an integer without a decimal. Now, I like to be very explicit, so I do 0.0. Some people do it like this. I don't like that, so I'm going to do 0.0 like that. Okay, let's run this again. Okay, so now we're where I would expect to be, where it's just the SDF march function is missing. So let's fix that. So float SDF march, and we're going to take an origin point. Technically, it's not the technically it's the current origin. If we want to keep everything easily followable, then we see that SDF March is taking current origin here. So we might just want to call this current origin like that. So that way in the source code, it's a little bit easier to see. And also, I realize that I'm being really stupid here. I have my names backwards because this is our iterative loop right here, right? This is the actual array marching algorithm, and yeah, I have this inverted. So SDF scene, and this is actually SDF march. So oh boy, I'm just confusing everyone. Okay, so SDF scene. So this takes a point in the scene and figures out the closest distance between this point and any other point of surface geometry within the scene. So it could be anything. The first thing to do here is let's just do this, make sure we... Okay, so they don't like that. I have this habit of doing double semicolons when I split a line. Like when the brackets are on a different line than where they start, I use two semicolons, and when they are on the same line as where the statement starts, I use one. So that way, if I see two semicolons, I know the statement started on a different line. That's just my kind of like convention. However, you can't do it here because different languages are more picky than others, but you're not allowed to have empty statements. Well, it depends on your version, but for this, I don't think they are allowing it. Anyways, SDF scene does not return a value, so let's fix that. Let's create... Eventually, I want to have two spheres, so let's say vec3 sphere 1. And we're going to have it at 0, 0, I don't know, let me think. So I'm going to do x. Let's do 0, -1 on the x. And 0. And 0, like that. Actually, no. And the radius is 1. So I just spaced that 1 out because I just want to know that it's kind of different. And let's just... Oh. So this is not my typical editor, so usually I use like Control-D for duplicate. That works in Notepad++, does not work in ShaderToy. So we'll have this on the left, so X, and then also this is, I am going to use, using a top-down camera, Z up. Okay, so there's different coordinate systems you can use. I like to think of the coordinate system as X and Y are like, you know, how you would draw it on a piece of paper, and then Z is like coming out of the paper. Different people do it differently. Like some people, like if I were to make a side scroller, X would be your character moving forward, Y would be your character jumping up, and then Z would be like going into the background to different layers of parallax. Some people will do it differently than that, but I think all the other ways are insane. Hence why I think that's why I like 3D Studio Max over Maya, because I'm pretty sure 3D Studio Max is Z up. Also, OpenSCAD is also Z up. I think Z up is just the sensible option, right? Like, we already work with 2D axes all the time. If you add a Z, you shouldn't change how X and Y work. You should just add a new dimension instead of shuffling it around. 'Cause a lot of people, they shuffle things around. I don't know why, but I think this is the simplest way to do it. So W equals radius. So if you're not familiar with ShaderToy or GLSL, you might not know what W equals radius means. But this is X, this is Y, this is Z, and this is coordinate W, X, Y, Z, W. Y is the last coordinate W. I have no clue. I don't know why. But look, you're at the end of the alphabet after Z, so you gotta go somewhere. Would A be more appropriate? I don't know, maybe, but then a lot of times people use A and B for, like, coordinates A and B, like vector A, B, right? So I don't know why W. Okay, so to get the distance to these different things, float, dist, you know what? I'm going to just call these I'm going to call it OBJ for object. And there's a reason for that, and that's because I don't want to think about how I'm going to name variables in the future. And I would just like to call this distance 1 for object 1, distance 2 for object 2. You may argue that the code is less readable this way, but I like everything kind of like normalized. I like everything kind of like as consistent as possible. So to get the distance from the origin to the sphere, we're going to take the vector from the origin to the sphere. So that would be object 01, the sphere, minus the current origin. And the way I think of it is I look at this, and I think of an arrow pointing to the left towards the object. And so it's current origin to the object, right? That's the way I think of it, to kind of remember which operand needs to be on the right or left when you're subtracting them, right? Because order matters with subtraction. So this is... So we have the vector to the center of the sphere, and then we take the length of that vector, which is the same thing as saying, this is the same thing as saying, what is it, distance, and then instead of using a minus, making these two different parameters, same thing. You may like to think of it one way or the other. I think it's important that you understand both ways, because not everyone's going to write code like the way you like to do it. So even though I wish there would just be one way to do things and we wouldn't have a proliferation of multiple ways to do things, even in math, there's multiple ways to express things. So this is the distance to the center of the sphere. Now, if the sphere was infinitely small, right, then we would be done, right? If it was just a infinitely small point in space. But it's not. It has a radius. So we need to back out from the center of the sphere. So to do that, we just need to reduce the length by the radius of the sphere. So we're going to do minus and obj01.w. Okay, and then it's the same thing for the other statement. I won't duplicate it just for the sake of getting some practice here. So sphere number 2, we're going to take the length of sphere number 2, and we're going to subtract it from the origin, right? Because it's the vector origin, arrow pointing to the left, origin to the object 2 being the sphere, and then we need to subtract the radius of that sphere. Okay, so now that we have the distance to these two different objects, what now? Well, when you're ray marching, you want to always be conservative in your distance estimates to geometry. So we will take whatever distance is shorter, and that will make it so that we avoid having our rays pierce through geometry. If you ever done like a sprite game, you know, if that your sprite is moving too fast, it can clip through walls. I'm pretty sure the same thing can happen in 3D as well. Something moves so fast that it can clip through walls or other solid geometry. Same thing with our ray marching algorithm. If we use a distance that is too large, we could accidentally clip through geometry. So for that, we just need to return the minimum of distances 01 and distances 02. And you can see that there's obviously a problem that needs to be solved when we have a whole bunch of geometry, because sure, this is going to be easy for 2 objects, but once we get up to, like, you know, hundreds of objects, this isn't going to cut it anymore. You're going to have to be clever and figure out how to kind of partition the space. I'm going to eventually, like, partition the space into, like, a 3D grid, and then figure out which grid cells the ray intersects, and then always have objects within a single grid. I kind of like to make like a 3D tile game. 3D tiles, also known as voxels. Okay, so that looks pretty good. But you know what? My ability to make syntax errors has never, what do you call it? Has never shocked me. We'll see, because you look at it, you're like, oh, that looks good, but maybe we screwed something up. Yeah, too many arguments, and then it's kind of obvious what you screwed up once you look at it, because a vec4, right? Because we supplied 4 arguments. It's we're thinking of it as a point in 3D space, but then we're adding this extra 4th component to store the radius, which I feel like maybe you don't want to do it that way, but I like the fact that it's less variables to keep track of. So let's refresh that, and now we have so it's an argument mismatch, so high p 4 component vector and float. Okay, so current object dot, like, sometimes when you look at these errors, it's like it's way too much information, and you have to like scan it to get the idea of like what are they saying. Because for this big block, I really don't want to read it all. All I need to do is scan it and go, okay, they're saying it's a problem with the types. I'm mixing types that don't belong together. And if I know that, that's all I really need, because then I can look at the code again and be like, okay, where am I making a mistake with my types? And then it makes it a lot easier, because object 1, once again, it has 4 components, but we only want to look at x, y, z when we're thinking about spatially where it is positioned in space. And same thing here as well. So let's run that again. Okay, awesome. So we don't have any, well, I mean, it's compiling. That doesn't mean we don't have any bugs. Okay, let's make some space down here. So now we get to test out our SDF march and see what's going on there. So let's just comment out, well, we could comment out call or we could just overwrite it. Let's just overwrite it for now. And that's lazy. It's not efficient at all to like render this gradient and then just blast it all the way. Actually, you know what? I changed my mind. Never mind. You know what? I think that I don't want to confuse anyone when they read my code. So let's just redeclare it, and we will call the march function. So SDF march. And now the question is, well, where is this ray coming from, right? Because we have an origin and we have a direction. And the origin is obvious. We'll just use the origin, but that direction is we still need to actually compute that direction. So so let's do vec3 org. This is like basically where the camera is, this origin here. And you know, maybe you want to we could call, no, we'll just call this origin and equals, remember that we have a top-down setup and we put the spheres at the origin. Well, we put the spheres at 0, 0, 0. So I want the camera to be kind of like looking down on the scene. So I just want to do vec3, and we're going to stay centered on the X and Y, but then for the Z, we're going to kind of look above like that. Okay. Now, from here, we need to, we know where the camera is, but the camera has to strike the screen in order to know like what pixel it's rendering. I don't know. I think of it as the camera origin is electron beam source, and then we have another we have like a phosphor screen in front of like a CRT monitor, right? And that's like it's kind of positioned right in front of the camera, but it's like a little bit lower down. Okay, so that's kind of like how I kind of think of it. We're not going to actually do much math with this. What we really need is just the 6 and the 3, or we need this, and we're just assuming that they're aligned with each other. If we wanted to like rotate the camera in space, we'd have to do more math, which I'm not super familiar with. Well, basically not familiar with at all. Let's be honest. It's been forever since I've done linear algebra. So that should be simple enough for now. So how do we get this direction from here? And so the direction is going to be going from that camera origin and passing through this like phosphor screen that's positioned here on the z-plane, and then its xy coordinates are actually the UVs. So this is just, so I just want to describe here, I'm just trying to describe a plane that is 3 in front of the camera with no rotation. So let's see, vec3 direction equals the vector from the origin to the phosphor. So the phosphor is over here, but it's not quite calculated like, well, actually, it's calculated like vec3 uv.x, uv uv.y, and then the phosphor screen dot z, like that. And then minus the orange. Okay, right? So the direction is from the eye or the camera, pointing left towards the current pixel on the screen that you're going through. So imagine like over here that the UVs, right? These are the pixels, but this is only two-dimensional. And we're going to describe where this is in 3D space. So we have this 3 right here that is kind of saying that we're going to turn this pixelated canvas into a kind of like a 2D piece of paper in 3 dimensions, so that we can kind of use this lighting model on it. So we can actually think of what we're seeing right here as the actual cells on our screen that that the rays are going to go through. I'm sorry if that's a horrible analogy. I'm not the best at explaining. Okay, so let's see. We got orange, we got dir. Let's give that a shot. Let's see what we got. SDF March. Those are both good. Oh, yeah, because, so I'm just going to call this hit, so I screwed that up. We got rid of color, but all we're really doing with the march is saying, did we get a hit or not? Now, we might want to get lighting information or not, and I don't know if it would be best to get the lighting information inside of March. And if that were the case, then we would probably want March to return a vec3, right, to have the actual color information. But I just want like the hit detection information, and that's kind of like what it's already returning. So let's not change that structure for now. And then right here, we'll return. I don't know if it can. I don't think it can. So hit, and hit. So grayscale, hit information. Let's give that a shot. Okay, so everything's black. Great. Okay, so we still don't know what we're doing. That's what this is. Now I guess we debug and kind of try to figure out where we're going wrong here. And that I really don't know. So what we could do is that, you know, I'm going to say the first thought is that maybe we just don't know what the hell we're doing, and this is over-engineered, and let's keep it simple. So, if, yeah, you know, just return 1.0 minus curl n, like that. Let's just do that. Let's just see what that happens there. Okay, so still no dice. From here, I guess the best thing to do would be to cross-check code I've written before and kind of see what's going wrong here, because it's like, what the hell? You know, I've watched these tutorials quite a few times. You think I would be able to get it in one go like this, but obviously not. So, origin to, yeah, that's, oh, you know what? I see what I screwed up already. So, the direction here is not normalized. Like these vectors, well, these vectors we're working with, right? Like this math right here, this direction times the length. You can't do direction times length if your direction vector isn't normalized. So, is there other stuff that needs to be normalized? Well, that's the only direction that we have calculated here. So I think that's all I need to do. So let's normalize. So just boom, normalize. And to normalize a vector, all you're doing is taking the vector and then dividing it by its length. So long-handedly, that would be take the vector, run the distance formula on the vector, and then after you've ran the distance formula on the vector and you get the distance, you take that distance value and you divide x by that distance, y by that distance, and z by that distance. So you divide each component of the vector by the distance of the entire vector, and that's how you normalize it. Doing that will always give you a vector that has a length of 1 while preserving whatever angle it has, or I guess direction would be a better word than angle. Okay, so let's try that out. See, oh, hey, look, whoa, we got something cool, awesome. Okay, now without any lighting, we can't really, without any lighting, we don't. Are these really spheres, or are they just circles? Right? Without any lighting information, we can't really be sure. So let's try to change some of these variables and kind of get the camera kind of moved further away. So I'm going to do this. I'm going to change this to, we're going to add 3 to each one of these to kind of take the same camera setup and just move it up. So without like changing if the lens is like wide or narrow angled, we're just going to move the camera. We're going to like dolly it up and kind of there. Now we got everything where we want it, right? And we know that they should be tangenting right in the center of the screen, because if we look at our math here, they're basically unit spheres, right? Because they have a radius of 1, and we moved this one over 1, and we moved this one over 1 to the other side. So does that make sense? Yeah, because the radius of 1, so it's the distance from here to here is 1. So it started, the one on the left started here, we translated it over here, and the one on the right started here, and we translated it over 1 to here. Okay, yeah, so that all checks out. So what we're seeing is correct. Now that we have figured that out, let's comment this out, and let's put back in our over-engineered code and kind of see if there's any difference. So we want this because we thought that maybe we would get some better anti-aliasing. It's going to be hard to tell, but let's just refresh this and kind of see if we have any difference. And you know what? I don't really see any substantial difference here. So for the sake of being efficient, we might want to just use this for now. For the sake of being efficient and just for having less complexity, right? Because when you're debugging and you see some crap like this, you know, that might get you worried. So keeping it simple and straightforward for now might be the best way to go. Okay, so from here, we need to calculate the lighting normals. And we need the light normals, but then we also need the surface normals, right? And we take the dot product of the surface normal with the light normal to get the amount of light that is hitting a given spot. Now, interestingly, or what I've always found interesting, or with the like Phong lighting model, and kind of like in general with lighting, the angle you view something at doesn't really change its lighting, right? In the lighting calculation, we're not really... We already know where the pixel is on screen, but your relative position to that pixel on screen has nothing to do with how bright or dim it is, which I found very odd the first time I realized that. But that's actually the way reality works. Like if you um a dark room and take a table and put some random objects on it and then get a lantern in front of it and then just walk around it and kind of see how the lighting plays, and you'll notice the lighting is it's very much a static physical kind of thing where you can just where it doesn't flux or anything when you move around it. I don't know how to describe it. I don't even know if that's making any sense. But but basically your viewing angle does not change the lighting. Now there are materials that the viewing angle does change. Um, the does change what gets to your eye, but most materials don't do that. Most materials don't have like any weird viewing angle optics. One of the exceptions to that would be like if you've ever seen that weird greenish pink paint they put on like sports cars, and it just looks like it's always changing colors because it it has a it emits a different color depending on how you're looking at the angle of the surface. So for a paint like that, you would have to have another normal, right? You'd have to have the surface normal, the light normal, and then also a normal from the surface to the lens. But we don't need that. And I was always surprised that we don't need the normal from the surface to the lens to calculate lighting for the most part. Um, anyways, I need to take a bathroom break. So what I'm going to do is I'm going to kind of set a timer. Oh, 420. Um, set timer. We'll do 8 minutes. And I'm just going to take that. And when that gets down to um, when that gets down to 0, then I'll be back. Taking my cup. All right. So I'm back. Let's finish this. So I just realized that SDF March are returning this hit value. If we're gonna do that, and then we're gonna call another function to calculate lighting, then we need SDF March to not return was it a hit, was it not a hit, like yes, no, Boolean kind of value. We need SDF March to actually return the distance from the origin to whatever thing it hit, if it hit anything at all. Now the problem with that is, well, SDF March, well, what if it didn't hit anything? Do we just return... Well, we can't return a 0 because that would just be hitting something right in front of it. We can't really... any number would be a hit. It would just tell us how far or close it was away. So I think that we need to take this vec3 and we're going to change this back to color. And then we can combine a vec3 with a vec4 and it'll expand out the x, y, and z. So this is the same thing as col.x, col.y, and col.z. So same thing. So this right here is the same as this. Okay, so then in SDF March, we're going to go up in SDF March. And we don't even want to return... well, right now, we can just return this for now. Just because that gives us something to work with. So we can see the results on the screen. And also got to change the return type of the function. Okay, so that's just a bit of refactoring. Because in here, I want to return... I want to figure out the lighting information. So what we'll do is we'll do SDF... do FDS light for the lighting. And we will use, so instead of org, it's going to be current origin, right? And then, also this variable right here can be hit. So, so basically we're going to do kind of like a lot of shader programming. It's kind of like branchless programming. So since the hit value is going to be 0 if no geometry is hit, we'll still calculate the lighting, but then we just multiply it by 0 to end up with black again. So I don't know if that's the best way to do it, but that's the way we'll do it. So float hit equals, and then yeah, we can still keep it a vec3 because we want to multiply each component of hit. Well, are we wasting memory if we do that? 3 hit times light. So vec3 light equals SDF light. And for the light, all we need to do is take the current origin. So it is yeah, because current origin keeps on being updated until we hit geometry or we go so far away from everything that we just give up. So for SDF light, let's just stub in a function for now. So we'll just call it vec3 SDF light. And vec3, technically it is still the origin. Do we want to call it org? Do we want to call it cur org? I don't know. I like when I'm only calling a function in one place, and I'm only calling this function in one place, then I want the parameter name to be exactly whatever it is in that one place that I am calling that function, right? Now, if I wasn't programming in such a small window, I would opt to just have this code inlined. I'm not for breaking things into smaller functions unless if the function is not called more than once, I don't see any reason to break it into smaller pieces. Because, oh, you think it makes the logic easier to follow? Yeah, it makes it easier to follow the logic on a high level scale. But then it just fools you into thinking you know what's going on because you go SDF light. I don't know what that function does, but oh, okay, well, makes sense enough to me, and then you keep on going. What if it was all linear? If we inlined this function, you could do the same thing where you see a comment where it says SDF light in the comment, and there's a whole bunch of code, and then you can kind of skim through that code and keep on scrolling down through the function. And even if you didn't do a detailed read of whatever this function includes, at least your eyeballs kind of skimmed over it. Whereas now when we look at this code, our eyeballs aren't even ever going to skim over this code. We kind of just forget about it and just pack it away somewhere. Also, when you extract things to functions, then it kind of wrecks the linearity of the code and just makes it harder to read. Makes it harder to read, makes it harder to conceptualize. So as a rule, I want the code to be so simple that somebody can follow it using, Microsoft Notepad. Like, I don't think you should be needing any special tools to follow the code. If your code needs special analysis tools and autocompletes and things, then maybe your code is too complicated. Anyways, that's just my rant on how I think things should be done. You don't have to believe me. Okay, so right here, for the light, we're just going to return vec3 1.0, right? So full intensity for the light. And so we haven't really added any new functionality. We just want to make sure that we haven't broken what we had previously. So let's give that a shot. And looks like we froze something. Oh, so that looks like it's still... Okay, yep, that's still working. Now, I'm going to just change this to... Sometimes when things work too often and they don't break on me, I'm like, I don't know, man. So let's change this to 0.5 and see if we get a difference here. Okay, so we have confirmation that our code is actually working and that it wasn't a false positive. And now we can go on to calculating the lighting for this. So for this, we need two normals. The surface normal and the light normal. And how are we going to get the light normal? Well, we need some type of light in the scene. So let's do a vec3, and we'll just do LIG01, and light1 equals vec3, and we'll put it at 0, 0, so at the origin, but we're gonna put it exactly where the camera is. So if we look at where the camera is, it's like at 9 up. Yeah, the origin of the camera is 9 above the ground plane. So we're gonna put a 9, and then you'd be like, light emitted from the camera. That seems kind of eh. But what we're gonna do now is we are going to offset from there by another vec3, and we're gonna do cos of I time multiplied by some type of like radius away from the camera. So we could do, well, we know that these spheres right here are like, so this is like 2 units. I don't know how wide the screen is in units, but let's try to get like a light source that even though it's above this, it's orbiting outside of the boundaries. So we know that the radius here is 1, which means that this is 2, and this is 2, so that's 4. So we could have it like right at the edge right there. Uh, yeah, let's do that because I think we can always change it later. So let's do a radius of 2, right? So 1, 2, right? And that gets the diameter, and then it's going to orbit kind of around here like that. Okay, so let's look at where that code is. So I time times 2, and then sine I time, what am I doing here? Oh, what am I don't know what I'm doing. I time times 2, yeah, because this is the angle, and then multiplied by 2 is the distance. Cos for the x, sine for the y. You could invert that. It'll just change whether you're going clockwise or counterclockwise. So when you do cos and sine, which I think is pretty standard, that gets you counterclockwise motion. And if we did it the other way around, where this is sin and this is cos, then we would get clockwise motion. So we'll do that, and the radius is 2. And then for the third parameter, we're going to do, we're just going to do 0, right? Because these are offset. This is an offset from the origin. And we basically want a light source that's kind of orbiting around 0, 0, 9, right? And it's orbiting around 0, 0, 9 by moving on the xy, but it's not moving on the z. So since it's not moving on the z, we're going to have a 0. But it is moving on the x, and it is moving on the y in a circular orbit. Okay, so that looks good to me. Next part is we want the actual light normal. So vec3 light normal equals normalize, and we're normalizing the direction from the current origin to the light. So cur org minus, oh wait, my bad, light cur org, right? Because we're going from the origin to the light source. That's the direction the vector needs to point. Because the current origin is like on the surface of the material, and we're going to point towards the light. And then we need a surface normal, and it's vec3, we'll do Sn for surface normal. And for this, we're going to do SDF, not guessed normal. Hold on, I'm going to make a note here. It's called estimate normal. We're going to use an estimate normal function, which basically will sample multiple points close to the origin to kind of derive the curvature in the 3D space, and then that will get us, that'll help us derive the normal. Kind of like a, I don't know exactly how the approximation function works, but it's kind of like on this circle, if we wanted to know the surface normal of like right here in 2D, we would go a little bit over to the left on the circle, a little bit over to the right on the circle, and we draw a line. And then the perpendicular of that line between the 2 points on the circle is an estimation of the surface normal, right? And then the smaller the 2 points are on the path of the circle, the smaller the distance between the 2 points on the path on that circle, the better our estimate is. So if we did this point to this point right over here, right? We're kind of way off because our surface normal is now pointing to the right, but well, I guess depends on, well, if we're calculating it for this point, I guess it would still work. Um, but if we were trying to calculate for this point and we use this point and then this point over here, that wouldn't be very accurate. But if we are trying to calculate the normal for this point and we use something a little bit to the left, a little bit to the right, draw a line, and then get the perpendicular, that would be a good surface normal. Anyways, I'm going to call it SDF est norm for estimate normal. And the surface normal estimation, all it needs is that current origin position. And we're going to try to do this from memory because I've seen it a few times. And so I want to see how much of the formula I kind of like remember from my memory. So this is a vec3. Okay, so from memory, what I remember is that you're doing a whole bunch of get distances, and it's like kind of like return normalize. I think it's return normalize, and then it's current origin minus it's like a vec3. 1, 2, 3. I think, I don't know if this is right. It's something like this. And then it's like, there's it's called get dist, well, SDF scene. So what we're going to do is I'm going to define S is SDF scene. This is also known as your get distance function if you've done this before. We're going to define E as epsilon, which is 0.001, something very small. Define X as cur org dot X, and define Y as cur org dot Y, and define Z as cur org dot Z. Okay, and so obviously that's a lot of defines, and then they all have to be undefined, which makes everything very bulky, right? And you probably don't want to. You might not want to type all that. Also, it adds a lot more lines to look through. You might think of it as like visual clutter. And I would do this a lot faster if I was working in my native editor, because I have column selection and whatnot. Column selection, column pasting. Okay, so the reason for that is this formula is somewhat complex, and I'm probably going to get it wrong. But then I'll cross-check against what it actually is. So there's some weird symmetry thing where we have like x minus s comma y comma z, and then there's also a, so there's something about like over here is negatives, and then over here there's like positives. So the same thing is going on over on this side, but it's like positive. So then we have like x plus s, and then a y, and then a z. And then for every iteration of whatever the hell we're doing here, we kind of slide over that s to the next thing like this. So this, and then z. And so there's kind of like this obvious pattern that kind of emerges. And why this comma is here right now, I don't know yet, because I honestly don't remember what operation goes between this. I'm just trying to remember the basic pattern I recall from looking at the formula. And then after I do as much as I can remember from memory, we're going to like cross-check it and see what am I missing? Because I know this isn't quite right, but I know that it's is the general pattern I remember. So basically by doing this, I'm going to help reinforce when you're trying to remember something, you have to figure out what you don't remember in order to remember, if that makes sense, right? So I've already been over this formula before, so by trying to do it from memory, I can get a better analysis and realization of what I don't actually remember. And so I do remember that there was a section over here where we're using the negative sign, and then there was a section over here where we're using the positive sign. Or it might have been flipped the other way around. I don't know. I also remember that my defines were like this, and it spelled out sexy Z. So, you know, when you have something that is kind of like a, what is it, an acronym? Or not an acronym. Well, kind of an acronym, right? Because each one of these letters does stand for something. So yeah, it is an acronym. But yeah, if your defines are an acronym, that can help you kind of remember things. And so I know that this part is right, correct. I know that this is correct. I know that this is a vague, amorphous idea of what the function is supposed to be. So now that I have kind of written everything that I can write, I'm going to do edit estnorm in my shortcuts to kind of bring up the reference and kind of cross-check it, see like where did I screw up, what did I do wrong, because I know it's not completely correct. So here in here I can see SDF scene. In another project I did, I call it SDF all geom, and so that's nice because by doing a define like this, right? S is used in a lot of places, but I have this leverage now where I can just replace this one token and the function will work. So I can kind of like cut and paste it into things. Here is my source for where I got this. So right here, this basic pattern of x plus e and the pluses moving down like this, and there's the columns, the x, y, and z. I have that pattern correct. What I don't have correct is that it is negative to positive, and then there's also a it's positive to negative, and there is also a negatives in the middle. So now that I know that, I can go back here, and these commas, right? I remember I was writing commas, and I'm like, I have no clue why I'm writing commas. I'm just taking a guess. I know some type of thing needs to be there. So that's what needs to be there. Now, we know that these are the positives and these are the negatives. And maybe we can remember it by thinking of plus and then minus minus. So one step forward, two steps back. Yeah? One step forward, two steps back. That's just me thinking of a silly way to remember it, you know. Hint. Okay, and so now let's just change around these signs. So let's just manually do it. So we'll go here, we'll go here, we'll go here, and then over here, let's just copy this sign here. And we'll change that. Okay, we got the Z, Y, X, Z, Y, X. That looks good. Now we need to make these all vec3s. So we just gotta put that in front. And we notice that we do have a constructor for a vec3, so we do need like commas in front of here because they're different parameters. I like to have the lax commas, having the commas in the front. because then the commas are in a more predictable place, whereas the line length here could change where the comma is going to end up. So here I just find more consistent. So I would say that cur org minus, I don't know if that's correct. I think that might be it. So let's look at here. So we are normalizing, and we are taking a vec3, but I don't see anywhere where we are taking this vector and then subtracting it from something else. It just looks like we're doing this. Now, I'm not sure if that's right. I mean, I've used this function. Like, I did have a bug in this function once, and I already tested it to make sure it works. But that does worry me a little bit. So what I'm going to do is I'm just going to check... I'm going to check the article. Oh, well, that's... let's just... it would be est norm log URL, something like that. Or est norm URL. Hold on. So I thought I had kind of archived what that was. Est norm. I am looking at my okay. So I try not to remember where all my references are from. So I try to put it in shortcuts, but anyways, so here's my reference. So let's go scrolling down here, find that formula. So there is a description of how we calculate the normal, and then it says that this is an approximation. And that looks about like what I wrote. So this right here confused the hell out of me, because this is a epsilon. It's not a this is not a member of operator. It's not a set operator or whatever. It does not mean member of. It looks a lot like another symbol. I'm not really good with my math symbols, but anyways, estimate normal, return normalize vec3. Okay, yeah, so that looks about right. Now I think I've seen this estimate normal function done a little bit differently before, and that's why I'm confused. But I know that this function works good, or gets desirable results. So I would say that for this, I'm happy with that. Except, you know, we gotta remove that. And cur org is, it is being used, right? Because the X, Y, and Z are actually coming from cur org. Okay, so that looks good to me. Oh, we do also have to remove one of these, put two of those in, and let's just give that a shot. Ooh boy. Vec3 normalize, too many arguments. Oh boy. Okay, well, let's approach it one at a time. So the first thing is that we need to create a vector with so if we look at this, do we have... Oh, really? Uh-huh. Vec3. Oh, yeah. Okay, well, plus, oh, okay, yeah, so I am, wow, okay, so I obviously did not remember that correctly. So first of all, it can't be plus s, because s is a function. So it's obviously, um, so this is what I'm talking about, remembering what I don't remember, right? Like, I kind of remembered the function, but I obviously got some things wrong. And then, instead of doing a vec3, what we're going to do is we're just going to say s, because s is the SDF scene function, and it will return a vec. Does it return a vec3? No, it does not return a vec3. It returns a distance. So this is a delta, and this is the x value. This other delta is the z value. Sorry, this other delta is the y value, and this delta, this last delta is the z value. So let's give that a shot, see what we got. Normalize operation result is undefined for the values passed in. So we're still screwing something up horribly. So I'm gonna guess that these errors up here are red herrings. Don't pay attention to that. We want to pay attention to SDF scene. SDF scene takes a vec3 and XYZ, yeah, XYZ. SDFC no matching overload function found. Oh, yeah, okay, so I see. So I'm doing SDF scene with like 3 arguments, and that's where I'm getting confused here. So we need the vec3 operator. So I was thinking it was either one or the other, and then I remembered incorrectly, but if we look here, yeah, there's a vec3 wrapper there, and then it's all wrapped in a vec3. Okay, so with that, we can kind of like fix that. So let's just say vec3, and then put another one like that, and we'll just kind of we'll paste. So paste that, we'll paste that, and obviously we'll have to fix this, add the parentheses where they belong as well. Okay, so now that we have that, let's add the closing parentheses where they need to be. Okay, let's give that a shot. Oh, so close, so close. Syntax error. So 1, 2, 3, and this is why I kind of like indent the way I indent, right? Because 1, 2, 3, right? And I already know what's going on there, right? Okay, so now that we have SDF S norm, we got a problem down here. No operation exists that takes float and int. Okay, so we're mixing float and int somewhere. So that's pretty obvious. These need to be 2.0, and this needs to be 2.0. And we could actually leave this as a 0 because I think this is in a vec3 constructor. So that should be fine there. Okay, so now that we have that, SDF light, I gotta say, I don't really see much lighting here. Oh, well, alright, because we still haven't done our calculation. So we got the light normal, we got the surface normal. But right now we're just returning 1.0 for maximum intensity. But we now need to do the math. So with the light normal and the surface normal, all you got to do is for vec3 light intensity, Li equals the dot, and does dot product care about the order? I don't remember. I don't think so. I think that's cross. Yeah, because dot will return 1 when the two vectors are perpendicular, and then when the vectors are, sorry, did I say perpendicular? Parallel. When two vectors are parallel, it will return 1. So that's like when a light ray is bouncing head on, you're getting the maximum amount of light energy, so it returns 1, right? So you know why it's warm in the summertime is because you get those direct rays of sunlight, right? And then if the rays are coming at you from really steep angles, then that value will get closer and closer to 0. So perpendicular returns 0 for dot product, and then parallel returns 1 for dot product. So I do not believe that with what I've just said, it does not make sense that dot product would care about the order of its operand. So let's take that and just make sure that we haven't screwed up the so obviously the intensity is a float, not a vector, and if I knew my math better, it would have been obvious because the dot product returns a scalar value. But like I said, it's been a long time since I've done linear algebra. Okay, so now that that is working, let's just try to return the light intensity and see if we actually have something that makes sense. Or, you know, it would just, you know, frickin'... Oh, I see. Got ya. So we still gotta do a vec3 with the light intensity. This is just so in case we want to have some type of texture or something on this lighting, or, you know, I don't know, maybe there's some material property besides a simple Phong lighting model and we want to return that, we can later. That's kind of why I returned it as a vec3. So we're just going to wrap the light intensity into a vec3. Okay, so now, okay, there we go. Okay, so let's see, our light it's up above, and it's orbiting around, and it's going counterclockwise. And I would say that looks pretty good to me. What we could do now is we could move where that light is. We could bring the light a little bit, we could bring the light down a bit. So let's bring the light down to like 3 and just see how that changes things. So, okay, I do like that. That looks a little bit, and also maybe let's change this to like, let's do these at like 4 or something. Okay, good. So now we have light, though I do say, why is the background white like that? I thought we had solved this problem. I'm gonna guess that somewhere in my calculation, I'm gonna guess this isn't actually white. This is probably RGBA with everything 0, and so since the alpha is also 0, this is like a completely transparent area, and it's just being displayed as white. That is my guess for what is going on there. So let's take a look at what our math is. So we have hit times light. Well, oh, okay. Yeah, I don't know. So what we could do is we could just, let's just take out the light for a second. Okay, white, and then this is black. So something about the light. Interesting. So something about, so our, when it's not a hit, like this isn't any geometry anywhere, I guess what's happening is that it's The lighting is saying that it's just No, I don't get it. I do not. Okay, so that is odd. I don't know why that is. But yeah, for whatever reason, it could be that this is getting what could happen is maybe this is getting an extremely high value. Maybe this is getting an extremely high value, and this hit value is actually an extremely low value. And because we're using the simple version of hit, we get a very low value multiplied by even higher high value, and then we get white. That's my guess of what's going on. So what we're going to do is we're going to comment out this, and we're going to put this formula back in. And we're going to do and it's float hit equals. All right, so we're going to try that and see if we get something different. Oh, excellent, excellent. So, because we capped it, right? I thought this might be a little bit too complicated, but now we see that this naive implementation here ended up with some just bogus results. So these results definitely look better. So we can make a little comment of, you know, we want to remember what we did before. Like if somebody looks at this and is like, that's way too complicated, why don't we do it this way? We'll have that in our code where we can remember the reason for why we did it the way we did it in the future. So with that, let's just compile it one more time because my screen kind of lagged, so I wasn't certain of if everything was going all right. What else? So now I think the last thing I want to do, because it's almost 2 hours, the last thing I want to do is I just want to animate these spheres. So object 1 and object 2, right, are our spheres. Let's I would like to actually get some evidence that these are. I want some more stuff to show me that these are actually three-dimensional objects. So let's do obj01.z plus equals, and we'll do the cos of I time, right? Because we got to animate it by time, and then we'll multiply it by a distance we want to move. So we'll say, let's just do like 3. So that's going to be 3 up and 3 down. And then we want the other one to be moving on a different phase. So we'll do object2.z plus equals the sine, all right? Because cosine and sine are complementary in terms of how they're offsetted, like their phase on a graph. Okay, let's just give that a shot, see what that looks like. And once again, I did this. Yeah, GLSL is pretty strict about that. Okay, so let's see. So that's coming towards you. Oh, now this one's coming towards you. Oh, okay. So that's nice. Okay. Now, what else? Let's I also do want these to Where do they cross? Okay, so they do cross. Okay, so we might want to like edit we might want to edit how that movement works later. Actually, let's do that now. So I'm satisfied. Like, oh, I see them getting bigger when they get close to the camera. I am satisfied that we've done everything. That these are definitely, three-dimensional objects. But I'm actually going to change this Z to X. And the reason for that is because the next thing I want to do is I want to do a smoothmin on the distance functions. I want to use smoothmin so that when these come together, they'll kind of like do some kind of like merging. Also, I'd really like to keep these on screen. So let's make that a little bit less extreme. So let's... Okay, so this... Okay, so they're close, far, so they have a decent thing where they're kind of like... Okay, so they have some decent distance on each other sometimes. And other times they get really close. So I like this right here. That's going to be enough for me to like test out what I need to test out. The next thing is the part that is in the shade is it's completely black. Let's just give it some diffuse, like a minimum. Well, is that diffuse or is that? Yeah, I think that's diffuse. Let's just give it a slight illumination in the dark areas. Now for that, we have SDF light. We can take we can do min 0.1 and then the light intensity, and that way it doesn't go all the way to black. And I can't calculate. I don't know why I always have trouble with min and max functions. But the light, we don't want the min, right? We want, yes, this is our minimum bound here. But if we're specifying a minimum bound, we want to use the max function. It's like complementary, right? So this is just saying that if this was a negative number or a very small number, well, since our max is this, then this is a clamp on the bottom range is what this is. So let's do that again. Okay, so now we see that the dark areas are kind of like, they're we can still differentiate the unlit part of the sphere from the background, right? And that's kind of what I wanted to go for. Okay, so before I close up, what I'm going to do is I'm going to take this code and I'm just going to copy it as, I'm going to copy it into my notes, and then I'll also put it on Pastebin. I don't actually think anyone is watching this stream, but I might as well put it on Pastebin just so that if anybody were to stumble upon my stream, then they'll be able to see it. So I'm going to save this in my learning folder as SDF3, SDF003. Okay, and then I'll just put that into SDF003. Okay, and now let's just go to Pastebin, www.pastebin.com. We'll just throw that code in there. Okay, and syntax highlighting is GLSL. I don't know why it's whatever. Never, and we'll just call this SDF003. And if you ever use Pastebin, the thing that really confuses me here is you want to hit this button once you're ready, not this button up here. I've done this so many times where I filled out everything, and then I hit this green button, and it just nukes all of my work. Yeah, so it's this create new paste button. It's just weird because this is create new paste, but I also read this button as create new paste as well. So I think of them as the same button, but these buttons do different things. It's probably obvious to normal people, but to me, I'm just like, oh, I don't know. Okay, so now that I have this, that's not a very user-friendly URL, right? So that's a capital W, lowercase x, lowercase a, capital J, lowercase c, lowercase u, capital V, lowercase f. So WXAJCUVF, and the capital letters are W, J, and V. Okay, anyways, I guess I could, can I zoom in on this? Will the URL get bigger when I zoom? No, the URL doesn't get bigger when I zoom. So let me just, before, one last thing, like, I'm going to take that URL and I'm going to save it into my source. And then what I can do is I can just go over here and I can watch my editor explode on me, I guess. So that was not what where the... Okay, so I don't know where that went. Let's just do a file new. Okay, so this is the URL, right? If you want to check that out on Pastebin, that's where you would go. Okay, so with that, I think I'm good. It's it's closing in on 2 hours. I got somewhere where, you know, I've been watching these tutorials and I wanted to see how much I could kind of recreate from scratch without looking at anything. I obviously had to peek at some old code to get it working. But I'm satisfied that I've been making progress. So I think I'm done here. I have no clue where this is saving to. All right, later.